In the middle of the Pacific, a storm the size of Texas is spinning at 180 miles an hour. Its pressure has collapsed to 896 millibars. Its winds have reached the theoretical ceiling for any cyclone on this planet, and it is aimed directly at American soil. Satellites tracked it exploding from a weak disturbance to a Category 5 monster in barely 2 days. A hospital will flood. An island's green will vanish. A 500-mile storm will crawl, not race. If this is useful, like and subscribe. What you're about to see is real, recent, and only the beginning. A Category 5 typhoon formed in April. That sentence alone should not be possible in most years. April is supposed to be a quiet month in the Western Pacific, the dead stretch before the real season wakes up. The waters are warm, but the atmosphere is usually too unsettled for a monster to organize itself. Storms form, but they wobble. They start, then fall apart. They rarely grow teeth. Sinlaku grew teeth in 2 days. On April 10th, a weak cluster of thunderstorms drifted near Chuuk, in the Federated States of Micronesia. It was nothing anyone should have feared yet. A minimal tropical storm, a smudge on the satellite map. By the afternoon of April 12th, that smudge had wind speeds of 150 miles an hour. By the early morning of April 13th, the Joint Typhoon Warning Center was measuring peak winds of 175 miles an hour. That is Category 5 on the Saffir-Simpson scale. That is the strongest category that exists. The National Weather Service issued typhoon warnings for Rota, Tinian and Saipan. These are the 3 largest islands of the Commonwealth of the Northern Mariana Islands. They're not foreign territory, they're American soil. About 55,000 people live on Saipan and Tinian alone. The warning language did not soften the reality. The forecast called for a devastating damage if the track and wind speed held. Sustained winds near the center were projected at 125 to 145 miles an hour, gusts to 160, and the storm was still tightening. Sinlaku was the second Category 5 tropical cyclone of the year on the entire planet. The first was Horatio, which spun in the South Indian Ocean in late February. 2 storms, 2 oceans, 2 months apart, both before the calendar even reached the usual spring warm-up. Meteorologists noted something else. Only a handful of Category 5 typhoons in the historical record have formed this early in the year. It is not unheard of. It is rare enough to matter. The satellite imagery made the rarity obvious. A tight, symmetric eye. A ring of intense thunderstorms wrapped around it. A pressure reading that kept dropping. The NASA GPM Core Observatory flew over the storm on April 12th and scanned it in 3 dimensions. What it saw inside the eye wall was a ring of rainfall so intense that it glowed magenta on the instrument display. That colour means the precipitation rate was off the top of the normal scale. This storm did not build the way most April storms build. It skipped steps. It went from a tropical storm to a super typhoon in less than 48 hours. That process has a name in hurricane science. It is called rapid intensification. And it is the single most dangerous behaviour a tropical cyclone can show, because it cuts the warning window for people in its path. The warning window for the Marianas was tight. President Trump approved emergency declarations for Guam and the Mariana Islands on April 11th, 2 days before the worst winds arrived. FEMA began moving people and supplies. Residents who lived in wood or tin houses were urged to evacuate to concrete shelters. The storm was not done tightening, and something in the water beneath it was feeding it at a rate forecasters had not expected. That is where the real story begins. On April 10th, Sinlaku barely existed. a slow-moving low-pressure area sat about 50 miles northwest of Chuuk, a small island group in Micronesia. Its winds were light, its structure was loose. If you had shown the satellite image to a forecaster without a timestamp, they might have guessed it was a dying system, not a newborn one. Then the clock started. Within 24 hours, the system tightened into a minimal Category 1 typhoon. By 1500 hours universal time on April 11th, maximum sustained winds had reached 100 miles an hour. The track turned northward. That direction put it on a collision course with the Marianas, and it put it over even warmer water. The real jump came next, from 100 miles an hour to 150 miles an hour in about 15 hours. Then from 150 to an estimated 175 miles an hour in about 12 more. That is a rate of intensification that leaves forecasters with very little time to update their public messaging. It leaves families with very little time to decide whether to board up a window or get in a car. The official term for this kind of growth curve is rapid intensification. The technical definition used by the National Hurricane Center is a sustained wind increase of at least 35 miles an hour within 24 hours. Sinlaku shattered that bar. Its intensification was explosive. What was happening inside the storm was almost textbook. The core of the cyclone was pulling heat and moisture out of the ocean surface. That heat fueled thunderstorms inside the eye wall. Those thunderstorms released their energy upward. At the top of the storm, the warm air spread outward and exited cleanly, because there was very little wind shear in the upper atmosphere to disrupt it. The result was a feedback loop. More heat in, more storms, more rising air, lower pressure at the surface, more heat drawn in again. Every part of the feedback loop was tuned for growth. Forecasters use a measurement called ocean heat content, which looks not just at surface temperature, but at how deep the warm water extends below the surface. Beneath Sinlaku, the warm layer ran far deeper than a typical April. That mattered, because as a hurricane stirs the ocean, it usually pulls colder water up from below. That cold water acts like a brake. It slows intensification. It sometimes stops it entirely. There was no brake beneath Sinlaku. By the night of April 12th, satellite analysis using the advanced Dvorak technique, an automated method for estimating storm intensity, suggested peak winds near 165 knots. That is roughly 190 miles an hour. Lightning flashes lit up the eye wall. Lightning inside the core is often a signal that a storm is still strengthening, because it points to intense updrafts rising faster than usual. The storm's central pressure dropped to 896 millibars. That number is the kind of reading that makes senior forecasters at the Joint Typhoon Warning Center stop talking for a moment when it flashes on the screen. It is in the lowest tier ever measured in any ocean. For reference, Atlantic hurricanes almost never get below 900. Something about the water beneath this storm was not normal. That anomaly was the real engine. Beneath Sinlaku, the ocean was running hot. Not slightly warm, not a fraction of a degree above average. Hot. Sea surface temperatures in the waters where Sinlaku intensified were measured at 30 to 32 degrees Celsius. In American terms, that is roughly 86 to 90 degrees Fahrenheit. That is bath water. And it is 2 to 3 degrees Celsius above the April average. In some spots closer to China, Taiwan and Japan, the anomaly ran even higher, more than 4 degrees above the long-term average. For a tropical cyclone, that is fuel stacked to the ceiling. The physics is simple. Tropical cyclones are heat engines. They pull warm, moist air off the ocean surface and convert it into wind. The warmer the water, the more moisture evaporates. The more moisture evaporates, the more energy becomes available to the storm. There's clear line in hurricane science, roughly 26 degrees Celsius, or about 79 degrees Fahrenheit. Below that number, tropical cyclones struggle to form. Above it, they can grow. Far above it, they can grow fast. Sinlaku crossed water that was 6 to 11 degrees Fahrenheit above that threshold. The warmth was not a single patch. It was a wide stretch of ocean running from the Caroline Islands north toward the Marianas. NOAA's coral reef. Watch satellites, which track sea surface temperature anomalies for reef damage, show deep orange and red shading across that entire corridor. Red on those maps means water that is running well above normal for the time of year. The anomaly runs deeper than the surface. Oceanographers measure what they call ocean heat content. This is a way of asking, if I pushed a thermometer down through the upper layers of the ocean, how much warm water is there in total? Not just at the top, but below. That matters, because a strong storm mixes the water beneath it. Colder water from below gets pulled up. In a normal year, that colder water shows up within a few dozen feet and slows the storm. Below Sinlaku, the warm layer ran far deeper than usual. That is the key. When a typhoon passes over shallow warm water, it cools the surface behind it and weakens. When it passes over deep warm water, the surface barely cools at all. The engine keeps burning at full throttle. There are two reasons the water was stacked this way. The first is a natural pattern. The Pacific has been in a La Niña state for most of the past 6 years. During La Niña, trade winds push warm surface water westward, piling it up near the equator west of the international date line. Years of that means years of heat accumulating in the Western Pacific. The second reason is longer. Global ocean temperatures set consecutive records in 2023 and 2024. That long-term rise raises the baseline. La Niña stacked warm water on top of an already warmer ocean. Sinlaku did not just benefit from those conditions. According to hurricane scientist Jeff Masters of Yale Climate Connections, it reached its maximum potential intensity. That is the theoretical ceiling of how strong any cyclone can get, given the water and air around it. That ceiling is almost never touched. This one touched it. Rapid intensification is the nightmare scenario in tropical meteorology. It is the reason forecasters cannot sleep the night before a storm reaches the coast. And it is the single hardest behavior to predict. Most tropical cyclones live short, uneventful lives. They form, they wobble, they strengthen slowly. Something eventually tears them apart. Dry air, wind shear, colder water, an encounter with land. The majority of systems that reach tropical storm status never make it to a Category 3, let alone a 5. A small number of storms do the opposite. They find perfect conditions and they explode. The conditions that let a storm explode are known. They're just rarely all present at the same time. There are 4 main ingredients. First, very warm water running deep. Sinlaku had that. Second, low wind shear in the upper atmosphere. Wind shear is the change in wind speed or direction with altitude. High shear rips the top off a storm. A cyclone needs its warm, rising core to stack straight up, like a chimney. If the winds aloft are blowing sideways at high speed, the chimney tilts and breaks. If the winds aloft are calm, the chimney holds. Sinlaku had calm winds aloft. Third, a moist atmosphere surrounding the storm. Dry air wrapping into a tropical cyclone acts like poison. It kills thunderstorm activity and hollows out the core. Sinlaku was embedded in unusually humid air. Fourth, strong upper-level divergence. That is a fancy way of saying the air at the top of the storm was spreading outward efficiently, like smoke rising cleanly out of a chimney. When that outflow is strong, it lowers the surface pressure beneath it, and the storm tightens. All 4 ingredients were in place. That is rare. There is a 5th factor that matters too: time. A storm needs to sit in those conditions long enough for the feedback loop to run. Some cyclones find warm water but move too fast over it. Others stall at bad location. Sinlaku had room. It had open ocean ahead of it. It had days before it would brush any land. The result was a feedback loop running at full speed. Warm water evaporates into the storm. Moisture condenses inside thunderstorms. The condensation releases heat. The released heat makes the thunderstorms rise faster. Faster rising air means lower pressure at the surface. Lower surface pressure pulls in more wind. More wind means more evaporation from the ocean. The loop tightens. This is how a 70-mile-an-hour tropical storm becomes a 175-mile-an-hour super typhoon in the time it takes a family to finish grocery shopping and drive home. The forecasting problem is obvious. Computer models often catch intensification late because the feedback loop is sensitive to tiny variations. A slight patch of dry air, a slight wobble, a slight tilt in the upper atmosphere, and the model predicts a different outcome. That uncertainty gets passed down the chain. Watches become warnings. Warnings become evacuations. Evacuations depend on the public trusting the number on the screen. When a storm doubles in strength in a day, public trust is tested. In the Marianas, the warning had arrived, but Sinlaku was about to do something that compounded every ingredient above. It was about to slow down. The most dangerous thing Sinlaku did was not its wind speed, it was its forward speed, or rather, the lack of it. Most typhoons that hit the Marianas move through fast. They arrive, they strike, they exit. The worst of the wind and rain passes in a matter of hours. That is the normal pattern. It is not a gentle experience, but it ends. Sinlaku did not end. Landon Aidlet, the warning coordination meteorologist at the National Weather Service in Guam, described the behavior as unprecedented for the region. On Saipan, tropical storm force winds persisted for more than 3 days. Typhoon force winds, which are sustained winds above 74 miles an hour, lasted for more than 24 hours. In his words, usually these things come through and move right on. This one did not move on. Robert Fenton, the FEMA Regional Administrator for Region 9, which covers Guam and the Northern Mariana Islands, offered the number that captured the scale of the problem. The storm was about 500 miles in diameter. It took 48 to 72 hours for it to move through. Think about what that means on the ground. Wind damage is not only a function of peak gust speed, it is also a function of how long a structure is exposed to high winds. Roofing materials can handle a single strong gust. They cannot handle strong gusts hour after hour after hour. Fasteners loosen, seams give, water works its way in. Things that held for the first 6 hours fail in the 12th. Things that held for the 12th fail in the 24th. The same is true for trees. A healthy tree can handle one sudden gust. It cannot handle a whole day of shaking. The roots tire, the soil around them saturates. Eventually the tree falls. The same is true for power poles, for utility lines, for cell towers, for roofs, for coastal dunes, for levees, for the patience of people inside shelters. Rainfall worked the same way. A short intense storm dumps rain on already dry ground. The ground can absorb some of it before flooding begins. But when heavy rain lasts for days, the ground saturates early, and every new inch of rainfall becomes direct runoff. Rivers rise, culverts overflow, low-lying areas fill like bathtubs. On the west coast of Saipan, the combination of rain and surge hit a lagoon area called Garapan. Satellite imagery and local reports showed massive waves washing across the bay and the lagoon. Coastal flooding warnings kept extending. Wave heights reached 25 feet for Tinian and Saipan. Freshwater flooding from rainfall and saltwater flooding from surge met in the middle, in the streets, in the homes, in the businesses. There is a reason Sinlaku moved so slowly. A tropical cyclone is steered by the surrounding winds at about 20,000 feet up. In the case of Sinlaku, the steering winds were weak. No strong system of high or low pressure was pushing it along fast. It drifted. That drift multiplied everything. The wind damage, the flood damage, the surge damage, the exhaustion of emergency crews, the time that water and wind had to work on weak points, and the strongest winds had not even arrived yet at landfall, 500 miles across. That was the diameter of Sinlaku as it approached the Marianas, the distance from New York City to Cleveland, the distance from Los Angeles to Las Vegas and back nearly. A single, rotating engine of wind and water larger than most American states. Size changes everything about a storm. A compact cyclone, even a very strong one, strikes a narrow corridor. The eye passes over a specific town. The worst winds hit a few miles on either side. 10 miles farther out, the experience drops to ordinary heavy rain. 20 miles out, it can feel like a distant thunderstorm. A large cyclone hits a region. Sinlaku was not aimed at one island. It enveloped several. When typhoon warnings were issued, they covered Rota, Tinian, Saipan, and the smaller northern islands of Alamagan, Pagan, and Agrihan. At the same time, Guam, more than 100 miles south of Saipan, was under a tropical storm warning and a typhoon watch. The outer rain bands reached Guam. The main core passed north of it. One storm, multiple American islands, multiple warning categories at once. The size of a cyclone is often overlooked in public conversation because the category number only tracks wind speed in the eye wall. Two storms can both be called Category 4. One might be 30 miles across, the other might be 300. The second will cause damage over 10 times the area. The second will require 10 times the emergency response. The second will keep winds blowing for many more hours at any given spot. For the Marianas, the size of Sinlaku meant that there was no hiding behind geography. On a smaller island chain, you can sometimes shelter on the leeward side of a mountain or on the far coast from the eye wall. That strategy does not work against a 500-mile storm. Every coast is exposed. Every valley funnels wind. Size also matters for the ocean. Large storms push a larger volume of water ahead of them. They build bigger swells. They generate wave energy over a wider fetch, which is the distance of open water the wind blows across. Longer fetch means bigger waves. Bigger waves mean more coastal erosion, more surge, more debris thrown inland by each crash. For Tinian and Saipan, the size of Sinlaku meant wave heights of 25 feet and coastal inundation of 4 to 6 feet in forecasts. That was layered on top of rainfall already in the ground. There is another consequence of a large storm that matters on islands: relief logistics. Guam and the Northern Marianas are not connected to any continental road network. Aid has to come in by plane or ship. The airports and seaports are clustered in specific locations. When the storm covers the entire island chain, the wind and surge damage the very entry points that aid is supposed to come through. The airport is flooded, the seaport is littered with debris. The runway is covered in tree limbs and metal. Getting help in becomes the first problem before help can even start. FEMA had pre-positioned supplies in Guam: 1.1 million litres of water, 723,000 meals, 5,300 cots, 3,600 blankets, 4,400 tarps, 78 generators. But those supplies were stored on the island that would take its own beating. The eye was now moving north. It was aimed at Tinian and Saipan, and what was about to happen at landfall would determine whether those stockpiles ever reached the people who needed them. Late on April 14th, local time, Sinlaku's eye reached Tinian, then Saipan. The core of the storm crossed both islands back to back in a matter of hours. This was the moment everything converged: the warm water engine, the slow forward motion, the 500-mile wind field, the saturated soil, the battered infrastructure. All of it came down on two small islands with a combined population of about 55,000 people. Saipan alone has roughly 43,000 residents. The wind speed at landfall, measured by the watchers and reported by the Joint Typhoon Warning Center, was near 150 miles an hour sustained at peak impact. Gusts were higher. The storm had weakened slightly from its open ocean peak of 175 to 185 miles an hour, but it had not weakened by much. Saipan Mayor Ramon José Blas Camacho described what the island was experiencing to the Associated Press while the storm was still active. He used plain words, "hitting us hard. It's so difficult for us to respond with this heavy rain. Heavy wind to rescue people. Objects are just flying left and right. Objects flying left and right is not metaphor. In a storm of this category, loose material becomes a weapon. A piece of corrugated metal roofing, once it tears off a house, becomes a sheet of steel moving at highway speed. Plywood becomes shrapnel. Palm fronds become blades. Small rocks become bullets. This is why residents of non-concrete homes are told to evacuate long before landfall, and why those who do not are warned that any debris becomes deadly. Landon Aidlet of the National Weather Service in Guam put the warning in terms no one on the island could ignore. Catastrophic damage. People in wood or tin homes should already be gone. Inside the eye, the experience was different. The wind fell. The rain stopped. The sky cleared. For about 10 minutes, in some parts of the island, residents who looked outside saw a ring of towering thunderstorms around them and calm air in the middle. This is the deceptive quiet at the center of every major hurricane. People who do not know what it is have been killed by walking outside during it, thinking the storm had ended. Then the back eye wall arrived. The back half of a tropical cyclone is often worse than the front because the wind direction reverses. Anything that was stressed from one direction during the first half is now being pushed from the opposite direction. Trees that leaned east all morning are now being shoved west. Roofs that held against a north wind are now being tested by a south wind. Structures fail in the second hour of the back eye wall more often than in the first hour of the front. By the time the eye had cleared Saipan and moved north, homes were gone. Cars had been lifted and overturned. Tin roofs had been peeled away. Utility poles had snapped. Trees had been stripped of every leaf. The only hospital on Saipan had water inside it. Major resorts had lost their backup generators. Roads across the island were impassable with debris. Power was out, water was out. And Sinlaku was still a Category 4 as it moved away. Every tropical cyclone has a ceiling. It is not a guess. It is a calculation. Hurricane scientists use a concept called maximum potential intensity. It is a physical limit derived from the temperature of the ocean, the temperature of the upper atmosphere, and the thermodynamic efficiency with which a storm can convert ocean heat into wind. The theory was developed by MIT atmospheric scientist Kerry Emanuel in the 1980s, and it is now a standard tool in tropical meteorology. The principle is straightforward. A cyclone is a heat engine. Its strength is limited by how much heat it can draw from the warm ocean and how efficiently it can exhaust that heat at high altitude. If you know the ocean temperature and the atmospheric profile, you can calculate the strongest wind that any storm could theoretically reach in that environment on that day. Almost no storm ever reaches that ceiling. Something always gets in the way. Wind shear nudges the core off its axis. Dry air gets entrained into the eye wall. The storm moves over slightly cooler water. An eye wall replacement cycle disrupts the inner structure. These small interruptions are the reason most Category 5 storms peak below their theoretical maximum and then weaken. Sinlaku hit the ceiling. According to hurricane specialist Jeff Masters at Yale Climate Connections, Sinlaku reached its maximum potential intensity during its rapid intensification phase. That is not a minor observation. It is a very specific claim. It means the storm was not just strong, it was as strong as the surrounding environment allowed any storm to be. The implication of that should be sat with for a moment. The maximum potential intensity is a moving target. It depends on the conditions available. In a cold ocean with dry air aloft, the ceiling is low, and no storm can become catastrophic. In a very warm ocean with humid air and efficient outflow, the ceiling is high, and a storm that reaches it will be among the strongest ever recorded. The ceiling beneath Sinlaku was high, abnormally high. That is not an accident of one day. The Western Pacific had been building toward that ceiling for years through a combination of La Niña trade winds piling warm water into the western basin and long-term ocean warming lifting the baseline. When a storm touches its maximum potential intensity, it is using every piece of available energy in its environment. It cannot become stronger without the environment itself changing. But the environment can change. If ocean temperatures rise further, the ceiling rises with them. A region that previously capped storms at 170 miles an hour can cap them at 180. Or 190. The numbers are not abstract. They are the difference between a tin roof holding and a tin roof becoming a projectile 3 blocks away. The theoretical maximum intensity in a warmer ocean is higher. That is physics, not opinion. For Sinlaku, the ceiling was already high enough to produce a Category 5 at an unusual time of year. The storm found that ceiling, leaned on it, and unloaded it directly onto American soil. What comes next is the single number that defines a storm of this class, not the wind speed, the pressure, 896 millibars. That was the central pressure inside Sinlaku's eye at peak intensity. To most people, it is just a number. To forecasters, it is a siren. Atmospheric pressure is the weight of the air pressing down on the surface of the Earth. At sea level, on a calm day, that pressure is about 1013 millibars. The air above your head, stacked all the way to the top of the atmosphere, pushes down with that much force. Most people never feel it, because they live inside it their entire lives. When a storm gets stronger, the pressure inside the eye drops. Air is being lifted upward and outward, faster than it is being replenished near the surface. The lower the pressure, the stronger the storm circulation has to be to pull air in toward that low center. Pressure and wind are linked. Low pressure means strong wind. The readings from the strongest storms ever recorded sit in a narrow range. Typhoon Tip in the North Pacific in 1979 dropped to 870 millibars. That is the lowest ever observed in a tropical cyclone. Hurricane Patricia in the East Pacific in 2015 reached 872 millibars. Super Typhoon Haiyan, which devastated the Philippines in 2013, was near 895 millibars. Hurricane Wilma in the Atlantic in 2005 touched 882 millibars. Sinlaku at 896 millibars sits in that company. Atlantic hurricanes almost never get below 900. The Pacific, with its wider ocean expanse and deeper warm water, produces more storms in the extreme low range. But even in the Pacific, a reading under 900 is uncommon. A reading in the 890s places a storm in the top handful of its basin's history. There is a practical reason forecasters react to these numbers. Pressure is a leading indicator of damage potential. A storm can hide its true wind speed from some satellite measurements because the eye wall is small and narrow. But pressure can be measured more reliably by reconnaissance aircraft and by the mathematical relationship between pressure gradient and wind. When pressure crashes fast, wind is about to follow. The rate of pressure drop in Sinlaku was dramatic. Over the course of roughly 24 hours, the central pressure fell from readings consistent with a minimal typhoon to readings in the deep Category 5 range. That kind of drop is called explosive deepening in meteorology. It is one of the clearest warning signs that a storm is still strengthening at the moment the number is read. There was another signal inside the eye wall: lightning. Lightning in the eye wall of a tropical cyclone is uncommon. Most of the thunderstorm activity in a mature hurricane is steady and warm, without the violent vertical updrafts that produce lightning. When lightning flashes inside the eye wall, it usually means something extreme is happening. Updrafts are accelerating. Ice crystals are being flung upward fast enough to generate electrical charge separation. Sinlaku's eye wall was lit up with flashes. For the forecasters at the Joint Typhoon Warning Center and the National Weather Service in Guam, the lightning, the pressure, and the symmetric ion satellite all told the same story. The storm had not finished tightening. On the west coast of Saipan, the water was about to start rising for reasons most people do not understand. On the west coast of Saipan lies an area called Garapan. It is the main tourist and commercial district of the island. It sits along a long, shallow lagoon that runs for several miles down the western shore. In calm weather, the lagoon is turquoise and nearly flat. It is protected by a reef that keeps the open ocean swell outside. During Sinlaku, the reef stopped protecting anything. Witness accounts and videos collected by the National Weather Service in Guam showed massive waves washing across the bay and the lagoon. The reef, which normally breaks down incoming swell, was overwhelmed. Water poured over it in sheets. The lagoon, which normally sits calmly against the shore, became a staging area for walls of seawater pushing inland. This is how storm surge works. A tropical cyclone does not simply pile up water under its eye. The wind field, wrapped around the low-pressure center, pushes surface water ahead of the storm. On the side where the wind is blowing toward shore, that water has nowhere to go. It stacks, it rises, it runs up the beach, it runs past the beach, it flows into streets, through the front yards of homes, into lobbies of hotels, into the lower floors of businesses. Storm surge is often the deadliest part of a hurricane, more than wind. Most storm-related deaths in major American hurricanes come from water, not air. For Tinian and Saipan, the coastal flood warning ran through noon Friday local time, with waves up to 25 feet and inundation of 4 to 6 feet forecasted. That is 4 to 6 feet of standing seawater above the normal high tide line. In some spots, the wave action on top of that surge was driving water even higher, with forecasts suggesting 10 to 15 feet. 10 feet of seawater is not survivable inside a typical home. Modern coastal buildings in the Marianas are often built on concrete pads with elevated first floors for exactly this reason. But infrastructure does not have that luxury. Roads flood, wells flood, water treatment plants flood, substation equipment which cannot operate in salt water corrodes instantly. The salt does not wash away when the surge retreats. It stays in the metal, in the soil, in the concrete. It keeps damaging things for months after the storm is gone. There's another mechanism making the surge worse. Rainfall. Sinlaku dumped extended heavy rain on Saipan. That rain was trying to drain off the island through the same low coastal areas where the surge was pushing water in. The two met. Fresh water from above, salt water from below. Where they met, the flooding was deepest and the drainage was slowest. Videos from the island showed roads that looked like rivers, cars submerged up to their windows, parking lots that had become brown ponds, tree limbs floating in what used to be intersections. In Garapan, the combination of lagoon overflow and inland rainfall ran into commercial buildings and resort properties. Some of those properties lost their backup generators to the water. Without backup power, the ability to pump out incoming water disappeared. The flooding compounded on itself. One of the first buildings to see water was not a hotel. It was the only hospital on the island. Saipan has one hospital. Just one. The Commonwealth Health Centre. It serves the entire island's population of more than 40,000 people, plus transfers from smaller neighbouring islands. If it goes offline, there is no nearby backup. The next full-service hospital is on Guam, a flight away. During Sinlaku, water got inside it. Ed Probst, a former lawmaker who works in the CNMI governor's office, confirmed to the press that the only hospital on Saipan suffered severe flooding. Major resorts also lost backup generators. In his plain words, conditions were pretty bad. A flooded hospital during an active super typhoon is a cascading emergency. Medical equipment is deeply dependent on electricity and on clean, dry floors. Dialysis machines need steady power and clean water. Ventilators need backup generators that are themselves dry and functional. Surgical suites need environmental control. Intensive care units need monitoring systems that cannot tolerate water intrusion into their wiring. When a hospital floods, staff have two simultaneous problems. They need to keep the patients they already have alive, and they need to keep accepting the new patients who are arriving, because the storm is injuring more people by the hour. Storm-related injuries during a landfalling Category 5 typhoon include things like lacerations from flying debris, blunt trauma from collapsing structures, drownings in flooded areas, electrical injuries from downed lines, and medical emergencies like heart attacks, which spike during high-stress events. Children with asthma struggle in the humid, mold-prone air of flooded shelters. Elderly residents with chronic conditions lose access to medications as pharmacies go offline. All of that flows toward the hospital. While the hospital is flooding, Tinian has one medical facility, not a full hospital, a clinic. After Super Typhoon Yutu in 2018, that facility was left structurally compromised. Similar patterns emerged after Sinlaku, with Tinian's medical capacity again strained and the ability to evacuate patients by air dependent on whether the airport runways could be cleared. Patient evacuation between islands is not a simple drive. There are no bridges. There are no inter-island roads. Moving a patient from Tinian to Saipan requires a boat or a plane. During an active typhoon, neither option exists. In the immediate aftermath, the airports and seaports are still clogged with debris. The ability of a hospital to function through and after a major hurricane depends heavily on preparation done years earlier. Backup generators, raised electrical panels, sealed ground floor openings, hardened windows, elevated fuel tanks. The amount of each of those investments made in the decade before a storm determines whether the hospital stays online. Saipan's hospital survived previous storms, partly because of investments made after earlier disasters. But survival is not the same as operating at full capacity. A flooded hospital on generator power is a hospital that is running at reduced function, with staff making triage decisions by flashlight while knee-deep in water. FEMA's regional response focused on this problem early. The US Army Corps of Engineers deployed its 249th Power Battalion to bring generators specifically to hospitals, airports, wells, and critical facilities. But before the generators arrived, the storm had already started revealing something else from the air. Something that could only be seen from a few thousand feet up. While Sinlaku was still pulling away from the Marianas, the US Coast Guard sent a C-130 aircraft up to get a look. Landon Aidlet of the National Weather Service in Guam was on the flight. The goal was simple: get an early visual assessment of the damage before ground teams could reach the worst-hit villages. A bird's-eye view of Tinian and Saipan while the storm was still pulling away to the north. What he saw, in his own words to the press afterward, was this. There was no green vegetation. It was all brown. What used to be thick, lush greens over the villages and the city area was gone. All brown, with only structures remaining. That single image explains more about a Category 5 storm than any wind speed number. Tropical island vegetation is dense, it is tall, it is layered. Palm trees, mango trees, flame trees, breadfruit, banana, ironwood, thick green canopies that cover the interior of Tinian and most of Saipan outside the built zones. These plants have survived typhoons for centuries. They bend, they flex, they loosen branches, they stand back up. They do not handle a 150-mile-an-hour wind that lasts for 24 hours. When the wind is sustained at that intensity for that long, leaves do not just tear off. They are ripped in bulk. The fine bark on trees is stripped. Small branches are snapped in quantity. Entire mature trees are uprooted. The shrub layer is flattened. Ground cover is torn away. What remains looks, from the air, like a brown moonscape. Only the structures stand up out of it. This is not a cosmetic problem. The loss of vegetation has immediate consequences for the next storm, the next rain event, even the next week. Stripped hillsides erode faster. Topsoil that held for generations washes out in a single week of post-storm rain. Freshwater streams silt up. Coral reefs, which are already under stress from warm water, get hit with a second blow when silt from the land flows over them. The tourism economy of Saipan depends heavily on the green. Visitors come for the contrast of turquoise lagoons against tropical hillsides. The destruction of that visual asset is not something that heals in a season. Palm trees take years to replace. Canopy trees take decades. In the interim, the landscape looks wounded, and tourism revenue reflects that. From the flyover, Aidlet also noted structural damage. It was going to be a tremendous loss for the island's vitality, and in the short term for tourism. There is a practical lesson from that flyover too. The speed with which the Coast Guard was able to get aerial reconnaissance into the air mattered. Damage assessment drives aid allocation. FEMA and the state response do not send equal resources to every village. They send more resources to the villages with more damage. The only way to see that at the speed disaster response requires is from the air. Drones are used for this in many contexts, but for a cross-island assessment on the scale of Tinian and Saipan, piloted aircraft still move faster and see farther. The flight confirmed what residents on the ground already knew. This was a direct hit from one of the strongest storms ever to reach American territory, and the American public, back on the mainland, was about to ask an uncomfortable question. Which American territory was this again? Most Americans could not find the Northern Mariana Islands on a map. That is a fact worth saying plainly, because it shapes how disasters in this part of the world get covered, funded, and remembered. The Commonwealth of the Northern Mariana Islands is a US territory in the Western Pacific. Its residents are US citizens. They pay federal taxes. They serve in the military at rates that are among the highest per capita in the entire United States. Saipan and Tinian are under the American flag. Guam, about 120 miles south of Saipan, is also a US territory. It is home to Andersen Air Force Base and Naval Base Guam, two of the most strategically important military installations in the Indo-Pacific. Together, these islands host tens of thousands of American citizens, active duty service members, and civilian contractors. They are American soil by every legal definition. They are also treated in practice as remote. The FEMA region that covers Guam and the Northern Marianas is Region 9. It also covers California, Nevada, Arizona, Hawaii, and a set of other Pacific territories. The regional administrator, Robert Fenton, was personally on Guam during and after Sinlaku. His team had been stockpiling supplies for this specific kind of event for years, because they knew that once a storm hits, the islands cannot be reached by road. This geographic isolation is the most important thing to understand about an island disaster. On the mainland, when a hurricane hits Florida or Texas, trucks can drive from Alabama, from Georgia, from neighboring states. Utility crews can roll in from anywhere in the country. Hospital transfers can be done by ground ambulance to an unaffected neighboring county. None of that works in the Marianas. Everything has to fly in or sail in. If the airport runway is flooded, nothing flies. If the seaport is clogged with debris, nothing docks. The pre-positioned FEMA supplies in Guam exist precisely because the alternative, flying them in after the fact, takes days that people without water and without medicine do not have. The logistical chain also works in reverse. Injured patients who need care beyond what the island hospital can provide have to be flown out. Medical evacuation flights from Saipan typically go to Guam, then to Hawaii, then sometimes onward to the mainland. Each leg is a plane. Each plane depends on weather. Each patient depends on a functioning airport. There is a political dimension too. Residents of US territories do not have voting representation in Congress. Their non-voting delegates can speak but cannot vote on final legislation. When disaster relief packages are negotiated in Washington, the political pressure that drives decisions in Florida and Texas is different from the political pressure that comes from a territory with no vote. This is not to say aid does not come. It does. FEMA's response to Sinlaku was rapid, large, and well coordinated. President Trump signed emergency declarations for Guam and the Marianas on April 11th, before landfall. The US Army Corps of Engineers deployed. The Coast Guard flew missions. Federal staff were on the ground. But the population-weighted attention is different from what a Category 5 strike on a state would receive. And that matters, because the recovery timeline is measured in years, not weeks, and the public memory fades fast. The Marianas have lived through this before, not long ago. In October 2018, Super Typhoon U2 struck Tinian and Saipan head-on. It was, at the time, the strongest storm ever to hit any US territory. Peak winds were estimated at 180 miles an hour. Gusts reached 215. It remains, by some measures, one of the most intense tropical cyclones ever recorded on the planet. Yutu followed a track similar to Sinlaku's. It crossed Tinian directly. It brought Saipan into its eye wall. The damage was staggering. Hundreds of people were left homeless. The Saipan International Airport was closed. The commuter airport was heavily damaged. Tinian, which had no ferry service and now had no functional airport, became logistically isolated. Residents could not easily leave. Supplies could not easily come in. South Korea sent planes to rescue its tourists trapped on the island. One woman was killed directly by U-2. Many more suffered indirect injuries and long-term health consequences from the aftermath. The recovery stretched into years. Children on Tinian went to school in tents. That last detail should land hard. In an American territory in the modern era, a Category 5 hurricane destroyed enough schools that children had to attend classes under temporary canvas structures for an extended period. Not a few days, long enough that photographs of tented classrooms became iconic. Landon Aidlet of the National Weather Service in Guam, commenting after U2, said the storm would set the scale for which future storms are compared. He was not exaggerating. Meteorologists in the region began treating U2 as a reference point. The building code changes implemented in the Marianas after U2 were designed explicitly with U2 in mind. Then, less than 8 years later, Sinlaku followed nearly the same path. This is the part that matters. 2 Category 5 equivalent strikes on the same small American territory in less than a decade is not normal. Before U2, the last Category 5 strength storm to make a direct hit on Guam was Super Typhoon Karen in 1962. That is a gap of more than 50 years between catastrophic direct hits. Then U2 in 2018, then Sinlaku in 2026, 2 in 8 years, both to the Marianas. The comparison is not identical. U2 was a classic fast mover. It came in, it destroyed, and it was gone. Sinlaku was slower, wider, and sat on the islands for longer. In some ways, the sheer duration of Sinlaku's damage may exceed U2's, even if U2's peak wind was higher. There is a pattern forming in the data that is not yet conclusive but is becoming harder to ignore. The Western Pacific is producing these extreme storms more often, and it is producing them at times of year when they used to be rare. Residents of Saipan who lived through both storms know this in a way that scientists are still quantifying. Their homes have been rebuilt once. Their neighborhoods have been replanted once. The trees that were replanted after U2 had just reached maturity. Sinlaku took them down again. On the ground, that is the rhythm disaster recovery now has to match. Not once a generation, once every few years. Guam, 120 miles south, watched Sinlaku pass with a very different outcome. Guam was not hit directly. That sentence explains almost everything about the difference in outcomes between Guam and the Northern Marianas. The track of Sinlaku shifted over its final 48 hours to pass just north of Guam. The island remained under a tropical storm warning and a typhoon watch. Outer rain bands swept across it. Flooding hit low-lying areas. Surge battered the coast. Debris blew through neighborhoods. But the core of the storm, the eye wall where the strongest winds live, passed offshore. The difference between a direct hit and a grazing blow in a tropical cyclone is measured in miles and hours. A storm eye that passes 20 miles away from a city delivers wind speeds that are often 40% lower than at the centre, and for a much shorter duration. A storm eye that passes over a city delivers the maximum sustained wind and exposes every structure to the full eye wall experience. For Guam, the narrow miss mattered enormously. Guam is home to roughly 170,000 US citizens. It hosts Andersen Air Force Base, Naval Base Guam, and a major port. A direct Category 5 hit on Guam would have consequences that ripple through American defense posture in the Pacific. Aircraft would have to be evacuated, naval vessels would have to be moved. The strategic cost, in addition to the human cost, would be immense. The last time Guam took a direct Category 5 hit was Typhoon Karen in 1962. More recently, in 2023, Typhoon Mawar came close. Mawar was expected to arrive as a Category 4 with possible strengthening to 5. The US military sent ships away. President Biden approved an emergency declaration. Residents in wood or tin homes were urged to seek concrete shelter. Mawar ultimately passed close to Guam, but did not deliver the full Category 5 direct strike that had been feared. Sinlaku was in the same pattern, close enough to cause real damage, far enough to leave the island standing. Marcus Landon Eidlet, the National Weather Service Warning Coordination meteorologist, described the post-storm landscape of Guam as debris-covered but survivable. Mud and broken branches covered roadways. Tropical storm-force winds caused hazardous conditions. Flooding hit low-lying neighborhoods. But the structural devastation that Saipan and Tinian experienced was not mirrored on Guam. The reason is geometry. A tropical cyclone's worst damage is concentrated in the eye wall, which is usually a ring about 10 to 30 miles thick surrounding the eye. Outside that ring, wind speeds drop off quickly. 30 miles out, the winds might be 30 to 40% lower. 100 miles out, the experience is more like a strong tropical storm than a catastrophic hurricane. The southern edge of Sinlaku's eye wall apparently did not quite reach Guam. That thin margin is why Guam's hospital was not flooded. It is why Guam's power grid largely held. It is why FEMA's distribution center on Guam was still functional after the storm and could serve as the staging base for aid to Saipan and Tinian. Had Sinlaku tracked 50 miles farther south, the Marianas disaster story would be inverted. Guam would be the flooded, roofless epicenter, and Saipan would be the forward staging base. 50 miles in the middle of the Pacific is nothing. It is the width of a good-sized county. Forecast tracks do not resolve differences that small reliably until the final hours before landfall. For the people on Guam, that margin was invisible. They prepared for a direct hit they did not get. For the people on Saipan, that margin was the difference between a storm that passed and a storm that settled in. The homes that stood through Sinlaku and the homes that did not revealed a rule that islands in Typhoon country have learned the hard way. In a Category 5 storm, the material of your walls determines the shape of your next morning. Concrete homes, poured with rebar and anchored to a slab, generally survive. Roofs may lift if not properly fastened, windows may blow out if not shuttered. But the box itself tends to hold. Tin and wood homes usually do not survive. This is not a new lesson in the Marianas. It is a lesson that has been learned, relearned and codified into law over the course of decades of direct strikes. The building codes in the Northern Mariana Islands are among the strictest in the United States for wind resistance, specifically because the territory sits in what meteorologists refer to as Typhoon Alley. Landon Eidlet, commenting on the aftermath of U2 in 2018, put it simply, "Building codes in the Marianas are tough because the storms are that bad. During Sinlaku, the pattern repeated." Robert Fenton, the FEMA regional administrator, noted that hardened infrastructure installed after past disasters held up well. Concrete utility poles, buildings constructed under the post-U2 codes. FEMA-built housing, which is often engineered specifically for hurricane-prone zones, remained standing. Older tin and wood structures did not fare the same. Del Benson, a resident of Saipan, described his experience during U2 in 2018 to the press at the time. "The skylight blew out. Then the roof started to go. They got the kids downstairs. The second floor of his home lost its roof entirely. The family rode out the storm on the ground floor. That pattern repeats during every direct hit typhoon. Families in non-concrete homes retreat to internal rooms, then to ground floors, then sometimes to shelters during the lulls. The luckier ones make it to public shelters before the storm arrives. The less lucky ones ride it out in structures that progressively come apart around them. One Saipan resident quoted after U2 described looking out a window and seeing his neighbour's wooden tin house completely gone. Not damaged, gone. A palm tree uprooted nearby. The neighbour's entire structure had been lifted and carried away in pieces. Modern concrete construction in the Marianas uses a specific set of features for typhoon resistance. Reinforced concrete walls poured with heavy rebar. Monolithic roof slabs, not truss and shingle systems. Hurricane-rated windows or shutter systems. Anchored foundations tied deep into the ground. These features add significant cost, but they also change survival outcomes during a direct hit. The problem is that not every resident can afford concrete construction. The Marianas, like many American territories, have a significant portion of the population living in older, pre-code housing. Wood frame, tin roof, single story, unanchored. These structures were common decades ago when such homes were what people could build with available materials. They have never been fully replaced. Every direct hit typhoon takes out more of these older homes. Every rebuilding cycle shifts the housing stock toward more concrete. The transition is slow, driven by insurance requirements, FEMA rebuilding grants, and personal savings. After Sinlaku, that transition is likely to accelerate again. Insurance assessors and federal rebuilding programs will push toward more hardened construction. Some families will use the opportunity to rebuild stronger. Others will leave the island entirely, adding to a slow population decline that has affected the Marianas for years. The physical survival of a structure is only one side of the equation. The other side is what happens when the power that runs that structure, that pumps its water, that lights its hospital, disappears for an extended time. Across Saipan and Tinian, that was about to be the defining question of recovery. Across Saipan, the power failed in stages, then failed completely. Utility poles snapped, lines came down, substations shorted out when saltwater surge reached them. Backup generators at major resorts ran until they flooded, then ran no more. By the time Sinlaku had pulled away, the grid across the northern Marianas was effectively offline. The timeline for restoration, in the words of officials on the ground, was measured not in hours or days but in weeks. Some hard-hit areas could be without power and water for weeks, one official told the Associated Press. That is not a dramatic worst-case statement. That is the realistic assessment based on the amount of physical damage to the transmission and distribution system. Restoring a power grid after a direct Category 5 hit is not the same as restoring a grid after a routine outage. In a routine outage, the lines are intact. A single downed tree is pulled aside. A breaker is reset. Power flows again within hours. After a super typhoon, the damage is not localized. It is distributed across the entire network. Every mile of line has to be inspected. Every pole has to be checked for integrity. Every transformer has to be tested. Every substation has to be assessed for saltwater corrosion. If any one piece of that network is still damaged, the segment beyond it cannot be energized safely. The US Army Corps of Engineers 249th Power Battalion is the unit responsible for deploying generators to critical facilities during disasters. During Sinlaku, the battalion prioritized hospitals, wells, airports, and critical public buildings. Generators are not a replacement for grid power, they are a bridge. They keep the most important services running while the permanent system is rebuilt. The problem with generator bridges is fuel. A generator needs diesel or gasoline delivered regularly for as long as it runs. On an island with flooded ports and damaged airports, fuel delivery is itself a logistical operation. The fuel has to come in by ship or plane. It has to be stored somewhere. It has to be distributed across the island by truck on roads that are often still blocked. Fuel scarcity becomes its own crisis. After U2 in 2018, Saipan residents reported shortages of water, electricity and fuel in the days following the storm. That pattern is the default, not the exception, after a direct typhoon strike on a small island. Communication infrastructure went down in parallel with the grid. FEMA reported that a major cellular tower system failed during the storm. FEMA communications teams deployed portable towers and antennas as replacements. Without that rapid replacement, residents would have been unable to reach family members, unable to call for medical help, unable to coordinate shelter or evacuation. For residents, the darkness that matters most is not just the literal dark, it is the information dark. Phones die, internet goes down, news becomes rumour, decisions about when to leave a shelter, when to check on a neighbour, when to try to reach a flooded relative get made with incomplete information. On an island that is fundamentally disconnected from the continental United States by distance, losing local communications is a second kind of isolation layered on top of the first. For the power crews, who in the end are the people who bring the lights back, the work is grinding. Repair cycles run from dawn to dusk. Crews rotate shifts. Parts have to be flown in. Wooden utility poles snap faster than concrete ones, which is why the post-U2 investments in concrete poles mattered during Sinlaku. But the island's fundamental problem during recovery was not only the power, it was what the absence of power was doing to the water. Water restoration is harder than power restoration. That's a fact about small island infrastructure that most people only learn when a disaster makes it visible. Robert Fenton of FEMA stated it plainly after Sinlaku. Restoring water was the most urgent need. In his words, the agency would focus on identifying which generators actually powered the wells and making sure those critical facilities came back operational as quickly as possible. To understand why water is harder than power, you have to understand how the water gets to a faucet in the first place. On Saipan and Tinian, drinking water comes primarily from wells. These are not simple hand pumps. They are deep wells with electric submersible pumps pushing water up from the aquifer, through treatment systems, into storage tanks, then out through distribution pipes to homes and businesses. Every stage requires electricity. When the grid fails, the pumps stop. When the pumps stop, the storage tanks drain within hours as residents keep using water. When the tanks drain, the pipes empty. When the pipes empty, they become vulnerable. An empty water pipe in the aftermath of a storm is not just inconvenient, it is a health risk. Empty pipes lose the positive pressure that keeps contamination out. When pressure drops to zero, groundwater and debris can flow backward into the pipes through any crack or open connection. When the system is eventually repressurized, it may be pushing contaminated water to every faucet on the line. This is why boil water advisories follow almost every major storm. After U2 in 2018, the Commonwealth Utility Corporation issued emergency boil water advisories across Saipan. The same pattern is expected after Sinlaku, while the distribution system is assessed pipe by pipe. Then there is the saltwater problem. Storm surge pushes seawater inland. That seawater does not just flood streets, it infiltrates the soil, it reaches shallow aquifers. On small islands, where the freshwater table sits only a few feet above sea level, saltwater intrusion can contaminate wells for weeks or months. Some wells recover, some do not. Bottled water shipments became the immediate bridge. FEMA's pre-positioned stockpile on Guam included roughly 1.1 million litres of drinking water, ready to move to Saipan, Tinian and Rota as soon as transport was available. That is a significant volume, but on an island with more than 40,000 people, 1.1 million litres is a matter of days, not weeks. Every litre of that bottled water has to be flown or shipped in, loaded onto trucks, driven over damaged roads, and distributed through points of distribution set up in parking lots and public buildings. Residents have to walk, drive, or be driven to those points. Elderly residents, disabled residents, and families with small children face a steeper barrier. Sanitation fails along with potable water. Toilets require water. Sewage systems require power. When both go down, human waste accumulates in homes and shelters. The disease risks that follow are real. Gastrointestinal outbreaks are a common secondary disaster after major tropical cyclones in populated areas. Showers, laundry, dishwashing, and medical sanitation all halt in parallel. The cascading inconvenience is exhausting. In a hot climate, with humidity staying high for weeks after the storm, the inability to bathe or wash clothes becomes a slow physical and mental strain on the population. For families who evacuated their homes, the crowding in shelters amplified every one of these pressures. And as the days after Sinlaku stretched on, those shelters were where the reality of the storm would settle in. More than 1,000 people were housed in shelters as Sinlaku passed through the Marianas. For a population the size of Saipan, that number is substantial. It represents families who could not safely remain in their own homes, either because those homes had been destroyed, damaged, or never were built to survive a storm of this size. The shelter network across Saipan and Tinian is not arbitrary. It is built around specific public buildings that have been hardened for exactly this purpose: schools, churches, community centres. These structures are constructed of reinforced concrete with shuttered windows and interior spaces that can accommodate large numbers of people temporarily. Inside, the conditions during an active super typhoon are tolerable, but not comfortable. The lights may be off, running on generator power or not at all. Windows are boarded. The sound of the storm outside is constant. High winds against a concrete building produce a deep vibration that residents describe as unsettling, even when they know the structure will hold. Rain pounds on the roof for hours. Occasionally debris strikes the outside walls with sharp cracks. Families bring what they can: blankets, a few changes of clothes, medications, infant supplies, phone chargers for the brief windows when a generator can power outlets. Some shelters allow pets, some do not. The families who cannot bring pets face an agonizing choice before the storm arrives. The shelter population is often drawn from the most vulnerable segments of the community: older residents without family nearby, single parents with young children, residents with medical needs, workers in temporary housing, tourists who were stranded on the islands when flights were cancelled. After the storm, these shelters remain populated. This is where Sinlaku's aftermath differed from a faster-moving storm. When a typhoon moves through quickly, shelters empty within a day or two. Residents return home, begin cleanup, and the shelters close. When a typhoon sits on a region for 3 days and leaves widespread destruction, the shelter population can actually grow in the immediate aftermath, as residents who rode out the storm in damaged homes decide they cannot stay. FEMA confirmed that shelter operations in the Marianas might be extended as power and water restoration continued. Jesse Apatang, quoted in reporting from the islands, urged residents to stay safe and work together. The pattern from previous storms is instructive. After U2 in 2018, FEMA situation reports listed 15 shelters with 934 occupants across the CNMY in the first week, with Saipan alone hosting 6 shelters at capacity. Within 2 weeks, occupancy decreased as power and water were partially restored, but some shelters remained open for over a month. This shelter rhythm is a hidden cost of island disasters. The social and psychological toll on families who spend weeks in a school gymnasium, eating distributed meals, sleeping on cots arranged in rows, cannot be measured in infrastructure damage figures. It shows up later, in mental health statistics, in school performance, in workforce participation. FEMA's Robert Fenton noted that the CNMI was requesting additional labour support as cleanup operations expanded. Shelter management is labour-intensive. Every shelter needs staff to maintain order, distribute supplies, manage medical needs, and coordinate with outside agencies. The supplies themselves have been waiting for this moment, stockpiled in a building on Guam that was about to become the most important logistics hub in the region. On Guam, in a FEMA distribution centre, sat the supplies that would keep Saipan and Tinian alive through the first weeks after Sinlaku. The inventory, as reported to Grist by a FEMA spokesperson, was specific. Approximately 1.1 million litres of water, 723,000 meals, 5,300 cots, 3,600 blankets, 4,400 tarps, 78 generators. 42 additional generators were already en route to Saipan when the storm was approaching. 90 FEMA personnel were on the ground in Guam and the CNMI before the storm made landfall. That number matters. Personnel cannot be surged in at the last minute. They have to be flown from regional offices, which takes days. Pre-positioning staff ahead of a forecasted storm is how FEMA shortens its response time from days to hours. This kind of pre-positioning is a relatively recent improvement in American disaster response. It emerged from the painful lessons of Hurricane Katrina in 2005, when the gap between landfall and effective federal response extended into a humanitarian crisis. Since then, FEMA has built regional stockpiles in strategic locations, including Guam, designed specifically for rapid deployment to Pacific territories. The stockpile is carefully calibrated. Water is the most essential item and the heaviest to transport, which is why so much of it is pre-positioned rather than flown in after a storm. Meals are shelf-stable and designed for distribution without cooking facilities. Cots and blankets support shelter operations. Tarps are for emergency roof repairs to keep rain out of damaged homes until permanent repairs can be done. Generators keep critical infrastructure running. 4,400 tarps is a telling number. It is a rough estimate of how many homes might need emergency roof coverage in the first weeks after a direct Category 5 hit. That is not a small fraction of the housing stock on Saipan and Tinian combined. The logistics of moving this stockpile from Guam to the other islands is its own operation. There are no roads. Everything travels by C-130 aircraft or by ship. After a direct hit on Saipan, the airport has to be assessed and cleared before military and civilian aircraft can land safely. Debris on the runway has to be removed. Navigation aids have to be tested. Fuel storage has to be checked. Once the airport is operational, the aid shipments begin. Aircraft fly in loaded with pallets of water, meals and generators. They land, offload, and return to Guam for another load. The cycle continues for weeks. Meanwhile, shipping containers are loaded at the port of Guam and sail to Saipan and Tinian, a slower but higher volume method of moving bulk supplies. The FEMI Region 9 response machinery, tested through previous storms, swung into action before Sinlaku even made landfall. President Trump's emergency declarations signed on April 11th unlocked the federal funding mechanisms that would keep the operation running for months. Beyond the federal response, faith-based and private aid organizations mobilized as well. Samaritan's Purse, based in western North Carolina, airlifted over 40 tons of emergency relief supplies to Saipan. The Salvation Army Hawaiian and Pacific Islands Division coordinated with the American Red Cross, the U.S. Army Corps of Engineers, and FEMA ahead of landfall. Getting the supplies into the distribution network was one problem. Getting the information about where they were needed was another, and for that, something far more fragile had already failed. During Sinlaku, a major cellular tower system on Saipan failed. FEMA confirmed this after the storm passed, noting that communications teams were setting up temporary towers and antennas to restore service. The failure of a single tower system on a small island is a different category of problem than a tower failing in a large American metropolitan area. On the mainland, neighbouring towers pick up the load. Signals overlap. Redundancy smooths over individual failures. On Saipan, with its limited number of towers and specific geographic coverage patterns, the failure of one major system means entire neighbourhoods go silent. Silent in the middle of a disaster is dangerous. Emergency calls cannot get through. Text messages to family members on the mainland fail to deliver. Elderly residents cannot reach caregivers. Medical personnel cannot coordinate patient transfers. Shelter managers cannot communicate with central emergency operations. The information networks that modern disaster response depends on simply stop working. There is also a psychological dimension. Residents of an island in crisis need to feel connected to the outside world. A phone that cannot make a call or send a message for hours or days is a profound isolation. Families on the mainland with loved ones on Saipan experience the same isolation from the other side. They cannot confirm that their relatives are safe. Rumours fill the gap where information should be. FEMA's response to tower failure is now a standard part of its disaster toolkit. Portable cellular towers, mounted on trailers with satellite uplinks, can be flown in and deployed within days. These towers provide basic voice and data service across a limited radius. They're not a permanent solution, but they restore enough connectivity for emergency coordination and for residents to reach family members. The sequence matters. Before cell service can be restored, the sites have to be physically accessible, roads have to be passable, power has to be available, either from a working grid section or from generators. Fuel has to be flowing. In the first days after Sinlaku, all of these conditions were in flux. Roads were being cleared hour by hour, generators were being positioned, fuel was being distributed. The communications restoration happened in parallel with teams setting up temporary infrastructure as soon as each site became reachable. There is a broader lesson here about the fragility of modern island infrastructure. Everything is interconnected. Power depends on fuel, which depends on ports, which depend on debris clearance, which depends on labour. Water depends on power. Communications depends on power. Healthcare depends on power, water, and communications. Hotels depend on all of the above to serve tourists. When one node fails, the cascade is immediate. When multiple nodes fail simultaneously, as happens during a direct Category 5 hit, the cascade becomes a system-wide collapse that has to be rebuilt node by node. The modern cellular network is the most visible example of this interdependence because so much of daily life now runs through it. A generation ago, when most communication on the islands relied on wired phone lines and broadcast radio, a storm damaged the network in different ways. Today, the damage is faster and deeper because the network itself is denser and more essential. For the Marianas, communications restoration became a race, not just to restore service, but to let an economy that runs on connections start running again. The stripped landscape Aidlet saw from the C-130, all brown with only structures remaining, had an economic shadow that was about to stretch for years. The Marianas economy has two main engines. Tourism is one, military and federal spending is the other. Sinlaku damaged both in different ways. Tourism depends on a specific visual and sensory experience. Visitors come to Saipan and Tinian for turquoise lagoons set against green hillsides, for white sand beaches shaded by palm trees, for a tropical environment that feels undisturbed. When the hillsides are brown and the palm trees are broken, the visual contract with the visitor is broken. That does not mean tourism stops. It means tourism slows, often dramatically, for the period it takes the landscape to recover. Palm trees can regrow their fronds in 6 months to a year after a storm strips them, assuming the trunk survived. Larger canopy trees, if uprooted, take a decade or more to replace. Coral reefs, if damaged by silt and storm wave action, can take longer still. Visitors who come during the recovery period see a wounded landscape, not the marketed one, and word of that spreads through travel reviews and social media faster than any tourism board can counter. The tourism infrastructure itself takes direct damage too. Hotels lose roofs, resorts lose backup generators, restaurants lose refrigeration, diving operators lose boats, tour operators lose vehicles. Each of these businesses has to rebuild with its own capital and insurance. Many do rebuild, some do not. After Super Typhoon U2 in 2018, Saipan's tourism industry took years to recover to pre-storm levels. The rebuilding required significant investment, and some older hotels that were heavily damaged chose not to reopen at all. The military side of the economy is more resilient but still affected. The federal government is obligated to maintain its installations. Bases are rebuilt. Housing for service members is restored. Supply chains are re-established. But each rebuild is expensive and takes time, and the time during which facilities are operating below full capacity has its own ripple effects. There is also an indirect economic cost that does not show up immediately in any chart. It is the slow migration of residents away from the islands after repeated storms. Every major typhoon that hits the Marianas is followed, in the months afterward, by a wave of permanent departures. Families who lost homes, who exhausted their savings, who cannot face rebuilding for the second or third time in a decade, relocate to Guam, Hawaii, or the mainland. Each departure is small individually. Together, they shift the population. The Northern Mariana Islands have been experiencing a slow population decline for years, driven by multiple factors. Repeated typhoons are one of those factors. U2 accelerated it. Sinlaku is expected to accelerate it further. A smaller population means a smaller tax base, a smaller workforce for the tourism and service sectors, and a smaller political voice in Washington for the territory. All of these feed back into the economic story. Robert Fenton of FEMA emphasized during Sinlaku's aftermath that the CNMI was requesting additional labor support. That request reflects the reality that the local workforce is stretched thin during a major cleanup, and many of the skilled workers needed to rebuild are already on the island, but themselves affected by the storm. The economic recovery will happen. The islands have recovered before. But the pace of recovery is being asked to match a pace of storms that is beginning to look different from the historical record. April storms are not supposed to look like this. That is the short version of why Sinlaku attracted unusual scientific attention. The Western Pacific typhoon season has no official start or end date, because tropical cyclones can technically form at any time of year in that basin. But the pattern of activity across decades of record shows clear peaks and lulls. Most typhoons form between July and October. A smaller secondary peak appears in November. The months of February, March, and April are typically quiet. Quiet does not mean empty. Storms do form in April. They're just usually smaller, shorter-lived, and less intense. The reason has to do with the seasonal rhythm of the atmosphere. In the early months of the year, the tropical Pacific is still coming out of its cooler season. Sea surface temperatures in the main development regions are warm but not at their maximum. The wider atmospheric circulation, including the location of the jet streams, the positioning of the subtropical ridge, and the availability of moisture is not yet in full typhoon configuration. In short, the engine is running, but not at full throttle. Category 5 typhoons in April are rare in the historical record. Not unheard of, but rare enough that meteorologists take note when one appears. Sinlaku was one of only a handful of super typhoons to reach that intensity this early in the year, according to meteorologists cited in NASA's coverage. What made Sinlaku possible was a specific alignment of factors that do not usually come together in April. First, the sea surface temperatures in the Western Pacific were running well above average for the time of year, 3 to 5 degrees Fahrenheit above recent averages in the region where Sinlaku formed, and up to 4 degrees Celsius above long-term averages in some nearby zones. Second, the atmospheric wind shear was unusually low, which allowed the storm to stack vertically and intensify. Low shear is more common in the height of the warm season, not in April. Third, the atmospheric moisture levels supporting the storm were high, and the upper level outflow was efficient. All of these factors aligned in April. That is the anomaly. There is a broader scientific question about whether early season Category 5 typhoons are becoming more common. The dataset is still small. Super Typhoon Haiyan formed in November 2013, Super Typhoon Meranti in September 2016, Super Typhoon Goni in late October 2020, Super Typhoon Surigay in April 2021 reached 190 miles an hour in the same region where Sinlaku formed. Surigay, like Sinlaku, was an April Category 5, 5 years apart, both in the Western Pacific, both breaking previous records for early season intensity. 2 data points do not make a trend, but when you add the broader context, the early season Category 5 count is climbing. Atlantic examples include Hurricane Beryl in July 2024, which became the earliest Category 5 hurricane in the Atlantic basin on record. Something is shifting in the seasonal distribution of the strongest storms. The exact mechanism is still being studied. One piece of it is almost certainly the temperature of the water beneath the storms, and the water beneath Sinlaku was not warm by accident. It was warm because of a particular rhythm of the Pacific that had been loading energy into the ocean for years. For most of the past 6 years, the Pacific has been in a La Niña state. That sentence is the most important piece of climate context for understanding why Sinlaku found so much fuel. La Niña is one half of the El Niño Southern Oscillation, or ENSO, the periodic shift in ocean atmosphere conditions across the tropical Pacific. During La Niña, stronger than normal trade winds blow westward across the equatorial Pacific. These winds push warm surface water toward the western Pacific, piling it up near the equator west of the international date line. Years of that westward push mean years of warm water accumulating in the western Pacific. The effect is not limited to the surface. Below the surface, the warm water extends deeper. As trade winds push the surface water west, the water column in the western basin thickens with heat. Ocean heat content, measured to depths of several hundred feet, builds up. This is a natural process. It has happened in every La Niña for as long as records exist. The western Pacific is always warmer than the eastern Pacific during La Niña, and the western Pacific always runs warmer than its long-term average during extended La Niña periods. What made the recent La Niña different was its duration. Multi-year La Niña events are not unprecedented, but a 6-year stretch with only brief interruptions is on the longer end of the historical range. That extended duration meant the warm water stacking in the western Pacific had more time to accumulate. The reservoir grew deeper and more thermally loaded than typical La Niñas produce. Then there is the second layer on top of the natural cycle. The global ocean has been warming for decades, driven by the long-term rise in atmospheric greenhouse gas concentrations. The pace of that warming has accelerated in recent years. Global sea surface temperatures set consecutive records in 2023 and 2024. When you take a natural La Niña pattern and run it on top of an already warming ocean baseline, the result is warm water stacked higher than any previous La Niña could produce. The baseline has moved. This is the setup that Sinlaku inherited, not an anomaly of a single week. A condition built up over years, concentrated in the exact region where the storm formed. The consequence is visible in the behavior of the storm. Sinlaku did not just intensify, it intensified to its maximum potential. The ceiling was high because the fuel was deep. When the storm tapped that fuel, there was no colder water below to slow it down. The brake that usually stops extreme intensification was missing. There is a concept in hurricane science called rapid intensification climatology. It measures how often and under what conditions storms undergo rapid intensification events. In recent years, that climatology has been shifting. Storms are intensifying rapidly more often, and the rate of intensification during those events is higher. The western Pacific, with its deeper and warmer water column, shows this shift as clearly as any basin on Earth. None of this is being claimed as a sole cause of Sinlaku. The storm would have formed without the long-term warming trend. Researchers cited in reporting on Sinlaku explicitly noted that the storm might have developed without climate change, but the warmer conditions increased the odds of rapid intensification and strengthened the storm once it was underway, and now the Pacific is about to swing in the opposite direction. That pivot is its own warning flare. After 6 years of La Niña, the Pacific is pivoting. El Niño conditions appear to be developing. El Niño is the opposite phase of the ENSO cycle. During El Niño, the trade winds weaken or reverse. Warm water that had been piled up in the western Pacific sloshes back eastward. Sea surface temperatures in the central and eastern Pacific rise. Global weather patterns shift accordingly. For tropical cyclone activity, El Niño has complicated effects that vary by basin. In the Atlantic, El Niño typically suppresses hurricane activity. Higher wind shear over the Caribbean and the tropical Atlantic makes it harder for storms to develop and intensify. Atlantic hurricane seasons during strong El Niños tend to be quieter than average. In the western Pacific, the effect can be different. El Niño conditions often correlate with more intense typhoons, even if the total number of storms does not increase. The warm water redistribution, combined with atmospheric changes, can create conditions favourable for stronger storms. Meteorological analysis of Sinlaku suggested that the emerging El Niño was part of the context for its intensity. Atmospheric scientists cited in coverage of the storm noted that the season was expected to be anomalously active because of a burgeoning El Niño. The combination of residual La Niña heat in the Western Pacific and the emerging El Niño pattern created a hybrid condition that was particularly conducive to intense early-season storms. If this transition holds, the forecast for the rest of 2026 is sobering. Forecasters are already treating Sinlaku as a warning flare rather than an isolated event. The combination of high ocean heat content, low wind shear, and the seasonal pivot into El Niño conditions is the kind of setup that has historically preceded very active seasons. The Atlantic forecast from Colorado State University, issued on April 9th, already reflects expectations of significant activity in that basin as well. There is a cautionary note here. El Niño conditions often bring record-breaking global temperatures. The warmest years on record have almost all coincided with El Niño events. As El Niño develops in 2026, global average temperatures are likely to push higher than the records set in 2023 and 2024. For the Western Pacific specifically, the pivot means that the warm water that had been piled up in the Western Basin will begin to redistribute. Some of it will flow eastward, some will remain. The exact distribution depends on the strength of the El Niño and the details of atmospheric circulation. Forecast models suggest that ocean temperatures in the main typhoon development regions will remain above average through the peak of the season in July through October. The combination of warm water developing El Niño and the lingering effects of years of accumulated heat creates an environment in which more Sinlaku-scale events are plausible. Plausible does not mean certain. Seasonal forecasts have significant uncertainty. But the physical conditions that drove Sinlaku are not disappearing in the near term, they are evolving. For emergency managers in Guam, the Northern Marianas, the Philippines, Japan, and the rest of the Western Pacific, the planning assumption has already shifted. The possibility of another Category 5 strike somewhere in the region during the coming months is no longer a low probability edge case. It is one of the more likely scenarios. The reason the Western Pacific holds this much energy is not just at the surface, it is deeper. Ocean heat content is the quiet variable in every major tropical cyclone story. It is the measurement that predicts intensification better than surface temperature alone. The concept is straightforward. Surface temperature tells you how warm the top layer of the ocean is on a given day. Ocean heat content tells you how much warm water is stacked below that surface, down to the thermocline, which is the depth at which temperature drops sharply as you go deeper. A tropical cyclone passing over the ocean does not just interact with the surface. Its strong winds churn the water column. Cold water from below mixes up toward the surface. If the warm layer is thin, the storm quickly cools the water beneath itself and loses fuel. If the warm layer is thick, the storm can keep drawing from it for days without significantly cooling the surface. The Western Pacific typically has a thicker warm layer than most ocean basins. That is part of why it produces more intense typhoons than most basins produce hurricanes. The physical geography of the region, combined with the prevailing wind and current patterns, concentrates heat in depth. During Sinlaku's intensification, ocean heat content in the region was extremely high. NOAA coral reef watch data showed anomalies that extended not just at the surface, but through the upper water column. The warm layer was deep enough that the storm's vertical mixing did not significantly cool its fuel source. This matters for forecasting. Storm intensity models that rely only on sea surface temperature systematically underestimate the intensification potential of storms over deep warm water. Models that incorporate ocean heat content, particularly those using data from satellite altimetry and from the Argo float network, do a better job. The Argo network is one of the underappreciated scientific assets of modern oceanography. Thousands of autonomous floats drift through the world's oceans, diving to depths of several thousand feet and reporting temperature and salinity measurements back to satellites. This network provides a three-dimensional view of ocean heat that did not exist a generation ago. Data from Argo and from satellite altimetry, which measures sea surface height as a proxy for ocean heat content, feeds into hurricane forecast models. During Sinlaku, these inputs showed extremely high ocean heat content along the storm's projected path. That information contributed to the forecast of rapid intensification, though the exact rate still outpaced model predictions. The implication of deep, warm water extends beyond any single storm. Surface water can cool relatively quickly, within weeks or months in response to atmospheric changes. Subsurface warm water lingers much longer. Once heat is stored in the upper few hundred feet of the ocean, it can persist for years, slowly releasing back to the atmosphere or being redistributed by currents. The heat stored in the Western Pacific over the recent extended La Niña is not going to disappear in a single El Niño event. Some will redistribute. Much will remain. The basin will hold elevated ocean heat content for an extended period, keeping the fuel available for intense storms. For populations in the storm paths, that persistence is the harder truth. A single anomalously strong storm can be treated as bad luck. A basin with persistently elevated ocean heat content over many years produces a pattern of intensification events that cannot be treated as random. There is one more atmospheric factor that almost always decides whether a storm explodes or dies, and during Sinlaku that factor failed at its usual job. Wind shear is the most common killer of tropical cyclones. More storms die from shear than from any other single cause. When meteorologists explain why a predicted hurricane fell apart before landfall, they are almost always pointing to an increase in wind shear that disrupted the storm's vertical structure. During Sinlaku, wind shear was absent. Wind shear in the tropical cyclone context refers to the change in wind speed or direction between the lower atmosphere, near the surface, and the upper atmosphere, typically around 30 to 40,000 feet up. If the winds aloft are blowing in roughly the same direction and speed as the winds near the surface, the shear is low. If they differ significantly, the shear is high. A tropical cyclone needs its thunderstorm core to stack vertically. Warm, moist air rises from the surface, condenses into storms and releases heat. That heat drives further rising motion. The whole column becomes a chimney. Low pressure at the base pulls in more warm, moist air, which fuels more storms. When wind shear is high, this chimney tilts. The top of the storm gets pushed off center from the bottom. The heat released by the upper-level storms no longer sits directly above the surface low. The feedback loop weakens. The storm struggles to intensify. If the shear is strong enough, it tears the storm apart entirely. During Sinlaku's intensification phase, vertical wind shear across the region was unusually weak. The upper atmosphere was calm. The storm's chimney stacked cleanly. Every thunderstorm that rose in the eye wall released its heat directly where it was needed to sustain the storm's structure. This is why the Washington Post's coverage of Sinlaku specifically identified weak wind shear as one of the classic ingredients enabling rapid intensification. Those are the conditions hurricane scientists have understood for decades as the most dangerous atmospheric setup for explosive deepening. Why was the shear so low? Several factors aligned. First, the subtropical ridge in the upper atmosphere over the western Pacific was positioned in a way that created a calm corridor over the storm's path. The steering winds aloft were gentle. The faster jet stream winds that often introduce shear were farther north. Second, the emerging El Niño pattern was beginning to shift atmospheric circulation in ways that can reduce shear over the western Pacific, even as it increases shear elsewhere. Third, the storm itself was generating a large outflow at its top that reinforced the low shear environment immediately around it. Strong upper-level outflow, in which air exits the top of the storm efficiently, creates a protective zone where incoming shear is less able to disrupt the core. All three factors combine to create an unusually stable upper atmosphere over Sinlaku during the critical hours of its intensification. The implication is worth stating clearly. When very warm, deep water is combined with very low wind shear, the ceiling for tropical cyclone intensity is effectively removed. The storm can reach its maximum potential intensity, which in the case of Sinlaku was a Category 5 super typhoon in April. This combination is not common, but it is not rare either. The Western Pacific produces it periodically. In a warmer world, the specific water temperature ceiling rises, which means the peak intensity during low shear windows rises with it. And the scale we used to describe these storms was built long before storms this strong were a recurring feature. It has a ceiling that Category 5 storms are now regularly testing. The Saffir-Simpson hurricane wind scale has 5 categories. Category 1 is the weakest, Category 5 is the strongest. There is no Category 6. That is not because storms cannot exceed Category 5. It is because the scale was designed with Category 5 as an open-ended catch-all for any storm with sustained winds of 157 miles per hour or higher. The scale was developed in the late 1960s and early 1970s by civil engineer Herbert Saffir and meteorologist Robert Simpson. Their goal was to communicate storm severity to the public and to emergency managers in a simple, actionable way. The 5 categories corresponded to different levels of expected damage to standard structures. At the time, Category 5 storms were rare enough that a single catch-all was sufficient. Storms with winds above 157 miles per hour were considered to be in a regime where almost any building would suffer severe damage, and the distinction between, say, 160 miles per hour and 190 miles per hour was less relevant for standard construction. That logic is being tested. Modern Category 5 storms routinely exceed the lower threshold of the category. Hurricane Patricia in 2015 reached sustained winds of 215 miles per hour. Super Typhoon Haiyan in 2013 had estimated winds near 190 miles per hour. Typhoon U2 in 2018 hit the northern Marianas with gusts estimated at 215 miles per hour. Sinlaku reached estimated peak winds near 185 miles per hour. These are not borderline Category 5s, they are well above the threshold. There has been ongoing scientific discussion about whether the Saffir-Simpson scale should be extended to include a Category 6. Researchers have proposed adding a new category for storms with sustained winds above 192 miles per hour. A 2024 paper in the Proceedings of the National Academy of Sciences argued that such an extension would better communicate the extreme hazard posed by the strongest storms, and noted that several recent storms would qualify. The proposal has not been adopted. The National Hurricane Center and other forecasting agencies have generally resisted changes to the scale, arguing that storms above Category 5 already represent a regime in which evacuation is mandatory and building survival is uncertain. Adding more numbers, in their view, does not change the actionable response. The counter-argument is that public perception of risk scales with the number on the category. A Category 5 sounds intense. A Category 6 would sound more intense, communicating that the strongest storms today are meaningfully stronger than the Category 5s of previous decades might change evacuation compliance. There is also a scientific reason to care about the distinction. The damage caused by a storm does not scale linearly with wind speed. It scales roughly with the square or even the cube of wind speed, depending on what kind of damage is being measured. A storm with 190 mph winds does not cause slightly more damage than a storm with 160 mph winds. It causes dramatically more damage. For the residents of Saipan and Tinian, the scale debate is academic. Their experience of Sinlaku was not defined by which category number appeared on the forecast. It was defined by the actual conditions they endured, which included sustained winds above 150 mph for over 24 hours. Those conditions are, for practical purposes, beyond the top of the scale that is designed to describe them, and Sinlaku did not begin its destructive path at Saipan and Tinian. Before it reached American soil, it had already done serious damage elsewhere. Before Sinlaku's eye wall reached American territory, the storm passed over the federated states of Micronesia. Specifically, it affected the Chuuk region, a group of small islands in the eastern part of the Caroline Islands chain. Storm surge battered Chuuk State before the typhoon moved on toward Guam and the Marianas. This is the forgotten stage of the Sinlaku story for most American media coverage, which understandably focused on the direct hit on US territory. For the people of Chuuk, the storm was catastrophic. The Salvation Army's coverage of Sinlaku's aftermath noted that flash flooding struck Guam and storm surge battered Chuuk State before the typhoon's eye passed directly over Saipan and Tinian on April 14th. The sequence of impacts extended across multiple Pacific nations and territories, with different conditions at each stage. Casualties were reported on islands other than Saipan, including Micronesia. Landon Aidlet of the National Weather Service in Guam confirmed this point in his interviews. The storm caused deaths in the region. The exact toll was still being assessed days after landfall, as communications with small outer islands remained limited. Micronesia does not have the same disaster response infrastructure as Guam and the Northern Marianas. It is an independent nation in free association with the United States, meaning American federal disaster response is available in some contexts, but not automatic. The government of the Federated States of Micronesia handles primary response to disasters affecting its territory, with international aid supplementing as available. Chuuk itself is a state within Micronesia, consisting of hundreds of small islands spread across a large lagoon. The population of Chuuk State is around 40,000, spread across those many islands. When a storm passes through, damage can be extremely uneven. Some islands take direct hits, others escape with minor damage. The logistics of assessing and responding to damage across hundreds of scattered islands are profoundly difficult. The smaller outer islands, with their limited communications, can be cut off for weeks before damage assessments become complete. Food supplies, which on many of these islands depend partly on subsistence agriculture and fishing, can be devastated when storm surge salts the soil and destroys crops. Recovery on these islands takes forms that differ substantially from recovery in a more developed area. The storm also affected other parts of Micronesia beyond Chuuk. The Pacific Ocean is dotted with small inhabited islands whose vulnerability to tropical cyclones is extreme. A Category 5 storm passing through can destroy an entire community's homes, water sources, and food supplies in a single night. International humanitarian organizations often respond to disasters in the smaller Pacific Island states, but the resources available are limited compared to the needs. The attention cycle of global media tends to focus on larger events in more populated areas. A disaster on a remote island in Micronesia can receive minimal coverage even when the per capita impact is severe. Acknowledging the pre-Saipan stage of Sinlaku's path matters for a reason beyond completeness. It illustrates that the storm was a multi-nation disaster, not just a US territorial event. The ocean and the atmosphere do not respect borders. A super typhoon that forms in the central Pacific and tracks northwestward will affect whatever is in its way, whether that is a sovereign nation, a US territory, or an independent island state. The statistical question of whether storms like Sinlaku are becoming more common is therefore not just a question about American disaster risk. It is a question about Pacific disaster risk broadly. Are Category 5 storms becoming more common? The honest answer is that the data is beginning to suggest yes, but the statistical case is still being built. Hurricane scientists distinguish between several types of possible trends: total storm count, peak storm intensity, rapid intensification frequency, seasonal timing. Each of these metrics can be analysed independently, and each tells a slightly different story. Total storm count in most basins has not shown a clear upward trend. Some basins show slight increases, others show slight decreases, and most are within the range of natural variability. Peak storm intensity is where the signal is clearer. The proportion of tropical cyclones that reach Category 4 or 5 status has been increasing in several basins, including the Western Pacific. Research published in the Proceedings of the National Academy of Sciences and similar journals has documented this trend across multiple decades. Rapid intensification frequency has also been increasing. Storms that gain 35 miles per hour or more in 24 hours have become more common in recent years, particularly in basins with higher ocean heat content. Seasonal timing shows some of the most visible shifts. Early season and late season Category 5 storms, historically rare, have been appearing more often. Sinlaku and Surugai in 2021 are both examples of April Category 5s in the Western Pacific. Hurricane Beryl in July 2024 became the earliest Category 5 on record in the Atlantic Basin. These shifts align with what physics would predict given warmer oceans. The maximum potential intensity of tropical cyclones is physically linked to ocean temperature. Warmer water produces higher ceilings. Higher ceilings allow more extreme storms when the atmosphere cooperates. The attribution of any single storm to climate change is a more complicated exercise. Researchers cited in coverage of Sinlaku explicitly noted that the storm might have formed without climate change. The existence of a storm is not itself proof of climate influence. What climate scientists can say with higher confidence is that the anomalous ocean warmth along Sinlaku's path increased the odds of rapid intensification and contributed to its peak intensity. Attribution science, a relatively new field, uses climate models to compare the observed probability of a given event in today's climate with the probability in a pre-industrial climate. For events like individual hurricanes, the attribution is probabilistic rather than deterministic. A storm like Sinlaku, under current ocean conditions, is somewhat more likely than it would have been under the cooler baseline of earlier decades. The Colorado State University Hurricane Forecast for 2026 Atlantic season, issued on April 9th, reflects these considerations. Forecasters are incorporating ocean heat content, wind shear patterns, and El Niño development into their seasonal outlooks. The expected activity levels remain elevated. For emergency managers, the statistical debate is less important than the practical implication. The probability distribution of future storms has shifted. The frequency of extreme events has increased. Planning assumptions that were calibrated to late 20th century storm patterns need updating. Whether that update is framed as responding to climate change or simply as responding to recent observed conditions, the practical effect is the same: more hardened infrastructure, more pre-positioned supplies, more robust evacuation plans, more redundancy in critical systems. The Marianas and every coastal region in typhoon or hurricane country will be making those updates. Some lessons from Sinlaku about which structures survived and which did not will shape those updates directly. In the aftermath of any major tropical cyclone, forensic analysis of building performance becomes one of the most valuable outputs of the disaster. Engineers examine which structures failed, which structures survived, and what specific features made the difference. For Sinlaku, the preliminary patterns were visible even in the first days after the storm. Concrete utility poles, installed as part of post-U2 hardening efforts, generally held. Wooden poles failed at much higher rates. This is a well-documented pattern from previous storms, and the investment in concrete poles after U2 paid off during Sinlaku in a directly measurable way. Fewer snapped poles meant fewer downed lines, which meant faster power restoration in the areas where concrete infrastructure was in place. FEMA built housing, constructed to specific hurricane-resistant standards after previous disasters, also performed well. Robert Fenton of FEMA specifically noted that hardened infrastructure installed after past disasters held up. This is not accidental. FEMA housing specifications include wind-rated roofing systems, hurricane ties connecting roof structures to walls, reinforced openings, and anchoring systems that transfer wind loads into the foundation. Modern concrete homes built to current Marianas building codes generally survived with manageable damage. Roofs were the most common failure point, with some losing sections of membrane or cap sheets, but structural walls held. Older tin and wood homes built before the current codes failed at much higher rates. This is where the most severe damage concentrated. Residents in these homes had been urged to evacuate to shelters before the storm arrived, and those warnings have been consistent for days. The specific failure modes of non-hardened structures follow predictable patterns. Roofs go first, usually starting with ridge caps or eaves where wind pressure is highest. Once a roof opening forms, the pressure differential between the inside and outside of the building increases dramatically, and progressive roof failure accelerates. Once the roof is gone, wall failure follows in structures that were not designed to stand without roof tie-down. Windows are the next failure point. Hurricane shutters, if installed and closed properly, prevent breakage. Unshuttered windows fail from wind pressure or from impact by airborne debris. Once a window fails, water enters the building and internal pressure equalizes with the outside, increasing stress on the remaining envelope. These mechanisms are well understood. The lessons for rebuilding are direct. Roofs need proper tie-down. Windows need shutters or impact-rated glass. Walls need continuous load paths from roof to foundation. Materials matter. For insurance and grant programs supporting post-Sinlaku rebuilding, these lessons translate into specific requirements. Rebuilt structures are typically required to meet current codes, even if the original structure predated those codes. Over time, this process gradually hardens the entire housing stock, one rebuild at a time. The trade-off is cost. Hardened construction is more expensive than non-hardened construction. In a low-income household, the additional cost can be the difference between rebuilding on the island and leaving. FEMA grants and Small Business Administration disaster loans help bridge this gap, but do not always cover the full difference. There is also a question of timeline. The rebuilding process after Sinlaku will extend over years. The initial phase of debris removal and emergency repairs takes months. The subsequent phase of full reconstruction takes longer. Throughout that period, the island operates at reduced capacity, with some residents in temporary housing, some businesses closed, and some infrastructure on backup systems. The lessons of Sinlaku will shape the next generation of Marianas construction, and forecasters are already looking past the current recovery to what the rest of the year might bring. Sinlaku is not being treated as the main event of 2026. It is being treated as the opening. The Western Pacific typhoon season does not officially peak until July through October. Sinlaku arrived in April. That timing alone suggests that the season may be unusually active. Multiple forecast agencies have issued outlooks suggesting above-normal activity for the Pacific Basin in 2026. The combination of residual La Niña heat in the Western Pacific, emerging El Niño conditions, and the broader background of elevated ocean heat content points to a season that will likely produce multiple intense storms. The Atlantic Basin forecast issued by Colorado State University on April 9th also reflects expectations of significant activity. The 2025 Atlantic season had 13 named storms, 5 hurricanes, and 4 major hurricanes, with 3 hurricanes reaching Category 5 intensity. The 2026 forecast anticipates continued elevated activity, though the exact numbers vary by forecaster. For emergency managers, the practical question is where the next major storm will strike. That is not knowable months in advance. What can be known is the probability distribution of where storms are likely to form and intensify, based on expected environmental conditions. The Western Pacific will remain a focus. The Philippines, Japan, Taiwan, and the Marianas all sit in the path of the region's typhoons. Each has experienced direct major strikes in recent years. Each is updating its preparedness accordingly. There is a practical vocabulary that has emerged for these shifts: hardened infrastructure, prepositioned supplies, rapid intensification preparedness, compound event planning, where multiple hazards like wind, surge, rainfall, and post-storm flooding are treated as interacting rather than separate. Each of these concepts is being absorbed into disaster response frameworks across the Pacific and beyond. In the Marianas specifically, the recovery from Sinlaku will overlap with preparation for the coming peak season. That overlap creates logistical challenges. Crews working on post-Sinlaku repairs may be the same crews needed for preparation ahead of the next storm. Supply chains that are flowing inward with aid need to maintain capacity for further inbound flows if another event occurs. The same pattern holds for Pacific countries outside US territory. The Philippines typically faces the largest direct impacts from Western Pacific typhoons, with multiple major landfalls per year in a bad season. Japan and Taiwan face their own exposures, particularly in late summer and early autumn. Vietnam and southern China are often affected later in the season as storms recurve or move westward. Sinlaku's specific track, which passed through Micronesia before hitting the Marianas, is one of several possible paths for Western Pacific storms. Other tracks move more directly toward the Philippines or recurve northward toward Japan. The specific steering winds in the upper atmosphere at the time of each storm determine which path it takes. Meteorological agencies across the Pacific are now monitoring the atmosphere for the next major system. The Joint Typhoon Warning Center, the Japan Meteorological Agency, the Philippine Atmospheric, Geophysical and Astronomical Services Administration, and other agencies coordinate through international protocols. Early warnings that a developing system might rapidly intensify get shared across the region. The lesson of Sinlaku, which is being absorbed by forecasters in real time, is that rapid intensification windows can open at times of year when they were historically rare. That lesson will shape the messaging for the next system whenever it appears. A single storm is not a trend. A single season is not a climate. The scientific caution on these points is genuine and important. What Sinlaku represents, though, is a data point that fits a pattern that has been accumulating across multiple basins for more than a decade. A pattern of earlier season extreme storms, a pattern of more frequent rapid intensification events, a pattern of storms reaching their maximum potential intensity over unusually warm water, a pattern of direct hits on populated areas at a frequency that is straining local recovery capacity. The Marianas have now taken 2 direct Category 5 equivalent strikes in less than 8 years. Before U2 in 2018, the previous direct hit at that intensity was Karen in 1962. The interval between catastrophic strikes has shortened dramatically. That change has implications that go beyond meteorology. Disaster recovery is designed for a certain expected frequency of events. Building codes, insurance markets, federal disaster funding, and local emergency response capacity all assume specific return periods between major events. When the return periods shorten, the entire framework has to adjust. In the Marianas, the adjustment is underway. Hardened construction, concrete utility poles, FEMA-built housing standards, pre-positioned supplies, regular exercises. All of these elements are designed to shorten the recovery time after each storm, because the gap between storms may itself be shortening. Beyond the Marianas, the same adjustments are being made across typhoon country and hurricane country. Coastal communities in the Philippines and Japan, in the southeastern United States, in the Gulf Coast, in the Caribbean, in Mexico, in Australia. The vocabulary of climate adaptation is becoming operational, not theoretical, not future, present. The science that connects all of this is still being refined. Attribution studies will continue to quantify the influence of long-term warming on individual events. Seasonal forecasting will continue to improve. Modelling of rapid intensification will continue to advance. But the physical reality is straightforward. Warmer oceans hold more energy. More energy available to storms means higher ceilings on peak intensity. More frequent warm conditions mean more frequent events that reach those higher ceilings. The basic thermodynamics is not controversial among researchers. What is controversial, or at least uncertain, is exactly how fast these shifts will proceed and exactly what they will look like in specific regions. The Western Pacific may see different changes than the Atlantic. The Indian Ocean may see different changes than either. Regional details matter. For the people on Saipan who are still cleaning debris from their yards, and the people on Tinian who are rebuilding homes for the second time in a decade, the broader science is less urgent than the immediate recovery. Their focus is on restoring power, on getting water back to faucets, on getting children back to school, on returning tourism to a level that supports local jobs, on whatever it takes to stand their community back up. FEMA's Robert Fenton said the islands were well positioned to recover because of their experience with these kinds of events. That statement is both encouraging and sobering. It is encouraging because the systems that have been built will work. It is sobering because the very existence of that experience and the deep familiarity with catastrophic storms that it implies tells you something about where these communities live. Sinlaku will not be the last. That is not a prediction. That is a description of the environment the Western Pacific now holds. The warnings are clear, the data is accumulating, and the ocean, still running warm, still holding its stored heat, is ready for the next event whenever it forms. The question now is not whether, it is when and where.